So you saw how that all worked together. That your television makes certain colors and then it just lines them up side by side. And each one of those three is a pixel. Now, if I want to make something HD, what do I need to do? If I need to make something HD, I want to have lots of pixels. So what do I do with each of those pixels? Each of those three, what do I have to do? If I want to have there be more of them, I've got to make them all smaller. And when they're smaller now, I can have more crisp edges and definitions and things like that. Now, there was a television a couple years back that boasted that their television has one extra color in their pixel, yellow. And they said, you know, all the other televisions only make 3 colors, ours makes 4. Ours makes its 4 colors, and it'll make by adding yellow, it'll make the colors pop more. Well, here's the problem with that. Not that their television didn't work, but what ultimately they were doing is they were saying, all of our televisions could make yellow, first of all. And if you want to make really bright yellow, you just up the red and the green and it'll make things more yellow. But what their television was effectively doing was it was taking their pixel, which was this big, and making it this big. So instead of this big, it was this big, and now they couldn't fit as many pixels. So they lost definition when they did that. Why would they do that? Because it sells TV. Because most people don't necessarily sit there and go, oh, well, what's the trade-off? The trade-off is a larger pixel, less definition. So it never took off, but you know what? I'm sure they sold a few extra televisions by pretending that they were on the cutting edge of what the next thing to come was. But the goal is to get smaller, not bigger. I mean, the next television could say, our television not only has yellow also, but it has magenta and cyan. And then you could blow it all the way out and have a pixel this big. Now where are you at? Big pixel. Okay. Now there's another thing called a complementary color. Complementary colors. These are colors that they tell you look nice, and then that those shoes look great with that stuff, makeup stuff. I don't know. All right. So complementary colors. What they are is a secondary color. We remember the secondary colors? They were, let's see, the primary were red, blue, green. The secondaries were magenta, yellow, and cyan. So if I take a secondary color, let's make it magenta. What's the missing primary? I've got magenta and I miss, the magenta is red and, is that red and blue? Red and blue. Which was the missing primary? I didn't say. So magenta is secretly red and blue. The missing primary would be green. So those two colors complement each other. It doesn't necessarily mean that if you wear magenta and green, those look good together. That's a style thing. That's a fashion thing. Those things change over time. But for physicists, secondary colors and a missing primary, that pairing, that marriage of those two, as they travel together, we would call those complementary colors. All right, the next one, I forget which is the next one I think it's going to be. Is it going to be yellow? If it's yellow, yellow is secretly what two colors? Red and green. So yellow would be red and green, and what color would be missing is blue. All right, now we have one secondary left that we haven't mentioned. We've got magenta, yellow, and cyan. So this is going to say cyan here. Cyan is secretly, in disguise, wearing its mask. Cyan is blue and green. So I got blue-green here. What color didn't I say? I've got blue-green is the secondary. The missing white, the missing primary color that would make white would be red. So cyan and red are complementary colors. All right. So look at that. Is that where yeah, we got a little bit more to go on this. Why is the sky blue? What lake is that? Anyone know? Bing, Crater Lake. All right. The sky is blue. I'm going to need a picture to help me explain. It's not because, let's say why it's not. It's not because the water is blue. It's not because the water is blue. The sky changes its color, doesn't it? It's not always blue. Sometimes it's red. Sometimes it's orange. Sometimes it's yellow. Sometimes it's gray. At night it's black. So, it's not because the ocean is changing its color. So the ocean doesn't cause the sky. The sky is changed, will reflect off the ocean. So if the sky is red, the ocean will be red. If the sky is gray, the ocean will be gray. The sky is whatever color it is. So, but the sky is the proximate cause. What is it that causes the sky to be blue? I'm going to need a picture to help me explain. Before we get to that picture, I guess we'll just say that the air is like little mirrors. And when light hits the air, it's been traveling through space, the void of space. When it hit the air, it's like, oh, I'm getting to hit something. I'm hitting atmosphere. I'm hitting atmosphere. The light's hitting atmosphere, and the light starts bouncing around. Some of the light gets bounced harder than other lights. Some of the lights gets bounced harder. Which light gets bounced the hardest? Blue light does. Because blue has the highest frequency of the three primary colors. There's red, blue, and green. Blue is the highest frequency. It's going, as it's going this way, it's going up and down really fast. Super fast, has the highest frequency. So it's going to hit more air on the ups and the downs as it drives forward at the speed of light. It's going to hit lots of air. While the red light kind of sneaks through the air a little bit better. It hits the air, but it sneaks through. Well, the blue light's going bing, 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 ow, 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 and it gets turned and thrown everywhere. As it gets thrown everywhere, that's what makes our sky. The light, the blue light in particular, splatters. It hits the atmosphere and goes splat across the entire sky. And that's why we have a sky. Imagine the moon. When you're on the moon, do you have a sky? No. What would be normal is not to have a sky. When you're in space floating there, and you say, and you look around, you don't have sky. You have black, 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 star. There's the star. That's where the light's coming from. It comes from there, but you look over here, it's black, over there it's black, and then you have the star. But since we have an atmosphere, even though the light comes from the sun, the light hits the atmosphere and goes splat. So now I look over here, and I don't see black. I see that light over here that got splatted over here, and that light got splatted this way, and this way, every which way, splatter. And so we have a beautiful sky every day, and I hope you go out and enjoy it every day, because I'm trying to keep you off your screens as much as possible. This part is necessary so you can enjoy the outdoors, because you can't do that without me. But when you go outside, the reason why you have a sky is because the light goes everywhere, especially the blue in particular. Now, if all three, red, blue, and green, splatted equally, well, then the whole sky would be white. And it kind of does that with the clouds, but with just the air, blue. All right. Now, why then, and this is going to help us understand skies even more, the sky even more, is when we talk about sunsets. And for that, I'll need a picture here. Look at that sunset. So now, but look here, we got this, two things here. Look at the sun is yellow. So the sun's supposed to be white, but it's yellow. If it's yellow, let's pause on this for a second. If it's yellow, what color is missing? Yellow. So yellow is that's it's supposed to be white, and so the complementary color, we got yellow is the secondary. Yellow is secretly red and green. Red and green. What color is missing? This is red and green light coming at us. Some color is missing. The blue. Where did the blue go? It splattered over everybody else's earth. This is our sunset time. Somewhere else, it's noon. Somewhere else, that blue light went splat, and this is the leftovers. The sunset's on the edge of the earth. I need a better picture. So let's go to, you can read the questions there. I need this picture. When you're bored, just read that stuff. All right. Here's home. Here is atmosphere. Here's the sunlight. I'm traveling through the void of space. I'm going really fast. All right, now splat. Splat, 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 splat. It hits all the atmosphere. It refracts. It slows down. They're even showing the bend, the refracting of that light as it hits. Old word there, right? Refraction. At this time of day, what time is it for this person? It's landing straight on top of their head. The sun is over there, the top of their head. The sun's landing on the top of their head. It would be noon for this person. And the sun, a lot of it hits the earth. We've got blue sky. Now the earth is going to rotate, but let's watch this person here. He's already enjoying his sunset. This was red, blue, and green. This is all the white light coming. Dun, 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 dun. It hits. Boom. They splat. The one that splats the most is blue. Blue goes all over. All right there. What two colors didn't splat as much? Red and green are left. They go a little deeper in. They're hitting and they're bouncing into all this atmosphere. And as they're hitting this atmosphere, the next color that goes splat is green. Now we have the red and the green that's making the sky go from blue to yellow. As the blue disappears, it's turning more yellowish because it's red and green. But the green is the next to get stuck in the mud and says, I can't go. You're leaving me. You're leaving me, red. I'm trying to hold on. But the green gets stuck. And so it mixes in with the red, makes yellow. But the red keeps going. And at the very end here, there's your red light. So what starts out as white, we subtract off the blue, it becomes yellow. We subtract off the green, it becomes red. We're peeling colors off until red, the longest wavelength, is the only thing left that sneaks through. And then eventually we're on the other side of the earth. And now it's dark. Does that make sense? I hope so. All right. Well, we'll find out when you read your book. So this is why the sky changes color. Now, if you have more pollution in the air, that's going to make this even more dramatic, more stuff to hit. The other thing to notice that I want to point out is look at the amount of atmosphere it's traveling through. At noon, the sun just cuts right through and hits you on the top of the head. There, I'm going to measure with my hand. It's right there. Well, we can do this guy down here. It's that much. But at sunset, look, it goes through 1, 2, 3 times that amount of air. That's why it's getting really tripped up. It's going through 3 times the mud of air, and so that's why you can even look at the sun. Because you're not supposed to look at the sun, right? But at sunset you can, because the light is traveling through 3 times. You have 3 layers of extra atmosphere here. So you normally just have this much. Oh, I burnt my retinas. Here, I have all that extra atmosphere as sort of a welder's mask. And not only is it blocking it, it's blocking it in phases. First the one color, first the blue leaves, then the green leaves, then the red leaves. But it gets less and less light, so it's easier and easier to look at. I think that's pretty neat. So when you've been drawing suns all of your childhood with those little happy pictures with the fields and the trees, and you drew the sun, you grabbed the yellow crayon most of the time. But that's because the blue got pulled out. The blue gets pulled out, and the red and the green are what hits this guy in the eyes, and this guy in the eyes, but the green gets pulled out. Well, then it's just red. As that green leaves, though, the colors don't just instantly change. They fade away one at a time. The blue just it slowly disappears, and then it slowly turns to an orange sun, and then it yellows to orange to red. It phases as the colors slowly drift out as it gets hung up in the mud there. All right. I was trying to say it in as many ways as possible. Why are clouds white? Here, because all of the light gets jumbled around. You say, why are they white? Well, all 3 colors must be present. Different size drops, big, medium, small, and when the blue light, the red light, and the green light hit, they all splat pretty equally, and then it just makes white. And then you got this water. Water's clear, right? But we have these white waves. We have all different size bubbles. If they're white waves, then that must be splattering the light equally, the red, blue, and the green. But this cyan there, people want to go to those white sand beaches for their honeymoons. Where do you want to go? I don't care. I just want to go to a white sand beach. Well, what does the white sand do? What's the point of what's wrong with brown sand? There's one down, we can just go to Lake Tahoe, brown, but I want white sand. What's so special about white sand? It's more reflective. Well, so what? What does reflective do? When the light, I'll pull some, let's see. Here, I'll pull it. When the light hits the white sand, all 3 colors bounce off pretty well. It's not perfectly white, but it's pretty bright compared to a brown sand beach. Now, if that water is if that sand, white sand is under the ocean, the light passes through the ocean, hits the white sand, and bounces back up into the air. And the water is brighter. with a white sand beach. Imagine if I took mirrors with me to the beach. Hello, it's me with my mirrors. All right, and I slide them under the water. Mirror, 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 mirror. Now when you look at the water's going to be brighter. It's like, wow, that water's so bright. But the colors are going to pop out even better than they normally do. Now, the color that gets stuck in water has a special, red has a hard time getting through water. Red has a hard time getting through water. So when the light hits, red gets stuck. The blue and the green bounce back out. The red gets stuck. The blue and the green bounce back out, and that is your cyan color. Now, if you have brown sand, the red still gets stuck, and then a lot of your blue and green get stuck, and it's just kind of, a lot of the green gets stuck, especially because it comes out blue and reflects back also. But what we want is as much light to bounce up, so you have that very bright beach. They have black sand beaches, white sand beaches. You can look it up on Google when you're bored. Black sand beaches from volcanic rock that's been turned into sand. But it's because of the light. You want as much light to pop out on those white sand beaches. All right. And then your art teacher would not list black and white as colors. They're pigments. Black is just really, really dark white. Gray is slightly dark white, and then black is like no white at all. So they're all white, but they're all just less and less brightness of it. We just darken the colors there until it goes to black. So they're considered shades because we're lowering them all equally. Maybe that's more of an art teacher thing than a science teacher thing, but hey, we try to support. Okay, next video, pigments.